So today, what we're going to do is introduce one of the modern applications of calculus. And that is differential equations. I bet you do. So, you know, there's actually a whole course at La Roche. I'm actually teaching it next semester if you're brave enough to take it, where we go in depth to study. I mean, it's still an elementary course in the big picture, but we cover a lot more than we're going to cover here in a class or two. But it is worth introducing you to it because many of you will encounter these when you take, for example, physical chemistry. And you'll encounter these in physics class, and some of you might in different biology or economics or finance. So what is a differential equation? Well, these equations differ from what you're used to. In the following way. In that now, the unknown is a function, not a number. Or numbers, I guess. We can be. So the unknown is no longer a function or the unknown is no longer a number or numbers, but it's a function or perhaps multiple functions. So we're going to show you what we mean by that in a second. So one of the phrases you've heard me say before is that mathematics is the language of science, and I'm not the first person to use that sort of phrase. In fact, many people would regard differential equations as the language of nature. They are, as the famous physicist, I believe it was Richard Feynman, said, Mother Nature speaks a language and it's differential equations. So those of you who might go on to learning more about math and physics or engineering, you will spend an awful lot of time studying differential equations. So let me sort of reiterate what we mean by what I just wrote on the previous page. So equations you've studied. So let's put them over here. So you've studied things like 3x plus 5 equals 10, or 4x squared minus 3x plus 6 equals 16. These are the equations that you've likely studied before. And the point with these is the unknown x is a number or numbers. So now let's compare these to some examples of differential equations. Well, maybe we are looking for a function f whose derivative satisfies that it's 10 times f. Or maybe we have a function f who's equal to a number times the variable x. Or maybe we have a function f whose derivative is equal to, maybe we'll say a second derivative is equal to the function's derivative plus 10. So here the unknown is the function. Or functions. So when you were a little peasant in what, 7th, 8th, 9th grade, when you first encountered algebra, you would have studied things along the lines of this. And I don't know how they motivated these things nowadays, but when I was a kid in school, we would start with even simpler and we would say, you know, what do we need to add to 7 to get 10? And then all the little peasants would say, oh, 3. And then you'd say, yay. Right? So you'd say 7 plus 3 is 10 or something. And so really when you first encounter equations, what you do is you talk about guessing and checking for an answer. And then as you become more comfortable with the language of algebra, you learn systematic ways of solving things. And you group equations. You call these guys linear. You call these guys quadratics or second order. And then you study all different types of polynomial equations, and you learn these strategies for solving them. Well, the study of differential equations is very much the same. So the goal of equations that you're familiar with is to determine which number or numbers makes it true. The same thing happens with differential equations. Only what you're asking is, what function makes this true? What function satisfies that its derivative is 10 times the function itself? Any comments, questions? If you've ever taken a physics class and you've heard of Newton's second law, force equals mass times acceleration. That is a differential equation. Yes?
For example, for that f prime equals to 23x, right?
Mm-hmm.
If we integrate 23x, we get
Right.
x.
You could, right? So what Shobit is recognizing is this equation seems to be able to be solved just by recognizing you can integrate, right? However, does that strategy work on the first one? No. Will that work on the second one? No, but you're correct. So that there's a bigger picture to that as well, and that is how do we solve algebraic equations? Well, and not even just algebraic, but transcendental equations like that have logs and exponents and sines and cosines. Is what you often try to do is your goal is to undo what's happening to the unknown. Right? So here, how would you solve this? You would say, okay, what's happening to x? You would say the first thing you're doing is multiplying it by 3. Then you would say you're adding 5. And so how do you reverse that? Well, then you would say, okay, let's subtract 5. And then what's the inverse of multiplying by 3? You divide by 3. And so there's some analogies with differential equations. If you look at this second one, you might reason similarly. Well, how do I undo the derivative? Well, I just integrate. And that, in fact, would work for this particular equation. But that strategy makes no sense here, and it makes no sense here. But that is a good observation, yes. So what we will do is we will look at 2 types of differential equations in this class. And they are, the first type we're going to study is what are called separable. And then the second type we're going to study are what are called first order linear equations. Now, I'm not going to lie to you. You do not have to memorize these words. And frankly, I'm not going to test you. I shouldn't say that. You should know how to solve these types. And it's snowing outside. Good grief. What in God's name? It's going to be 60 degrees in 2 days. Welcome to Pittsburgh. This is my favorite because then all the people who hate global warming, see, it's fake, right? And then in 2 days from now, all the people who love global warming will say, see, it's global warming. Huh? I like to make fun of people. Do you guys make fun of me when I'm not around? I bet you are. You're always like, oh, okay, this guy's an idiot. Someone's chatting it up. Oh, that sucks. Yeah, I was around a cat on Sunday, Emily, and then I was sneezing. Damn cats. I guess I don't know if that's seasonal allergy. But. So we will discuss what we call separable equations, and we will also discuss first order linear equations. So I'm assuming you're referring to the snow. Better not lay. All right, so let us jump right into it. So let's consider this creature that I have written, but let's write it in a slightly different form. So let's consider dy dx equals, say, 10 times y. So the first thing we need to note is context here says a couple things. It says first that y is the unknown function. And the function has an independent variable. And that's the letter x. So how do I know that that's what context says? Well, look at it, dy dx. Y is the dependent variable, or the function, the name of the function, and x is the independent variable. Now, there's a couple of things you could do here. You could do perhaps sort of what Shobit you were alluding to. This is an equation that is simple enough that, and when I use the word simple, I don't mean like fifth graders get this. I'm saying, relatively speaking, it is simple. Not to offend you if you don't think it's simple, simple relatively speaking. And this is one that is simple enough that you might be able to guess the solution off the top of your head. You might say to yourself, okay, what function would satisfy this? And you can start eliminating guys, because can y be a polynomial? And the answer is no, because here's what you know about polynomials. Every time you differentiate a polynomial, its degree goes down by 1. So there's no way on God's snowy earth right now that if I differentiate a function, the derivative can be 10 times what I started with. That doesn't make any sense. Okay, what other functions are we familiar with? Maybe you start saying, okay, I know polynomials are out of the woodwork. What about trig functions? You know, you might say to yourself, well, the derivative of sine is cosine, so maybe that works. But here we don't really have that, because this would say, this is saying dy dx equals 10 times y. So sines and cosines aren't really involved here. But what we start doing is we eliminate, we see, I do have a guy that might be a good candidate for a solution. Because one of the groups of functions we're very familiar with are the exponential functions. And they have this fabulous property that when you differentiate an exponential function, the original function shows up in the derivative. And so that means that this exponential function is a good candidate for this. So let me suggest the following. So some trial and error, or guess and check, might lead to guessing a solution of y equals, more specifically, oh yeah, we'll say y equals e to the 10x. Now, notice that dy dx is in fact 10e to the 10x, or if I replace, remember, e to the 10x is, by definition, another name for this is y. And so just like with algebraic equations, since it satisfies the equation, we call it a solution. Since plugging y equals e to the 10x into the equation makes it true, we say it is a solution. Notice I'm being very, very careful with my words. I'm saying it is a solution. I didn't say it's the solution. Now, I suggested this to you guys way back in Calc 1, if you remember. And one of the reasons the exponential function is so useful as a application in the real world is because it has this amazing property. Think about what this is really saying. It's saying that something's rate of change is proportional to its size. Well, hell, we see that. If you have a biology class and you put bacteria in a petri dish, the growth rate is going to be proportional to its size. If you put money in a savings account, its growth rate is going to be proportional to its size. What's going to make money quicker? $10,000 or $100? If we're talking about interest, for example. So this little scary group of symbols down here if interpreted in the real world, can be very applicable. Because again, I repeat, this says that the growth rate of something is proportional to the size of whatever we're studying its rate of change. What do you mean write it either way? I don't even know what you're saying with that, Emily. What do you mean by that? We're going to have to elaborate because I don't know what you mean by write it either way. What do you mean? I'm not plugging an equation into the other. I'm saying, let's guess that y is equal to e to the 10x. Let's guess it. And then if I take y in this equation down here, and instead of writing y, I put e to the 10x, and instead of writing dy dx, I put the derivative, then it's a true statement. I mean, the analogy here is no different than if you go back here and you wanted to check that your solution to this was correct, you plug it in. How do you know that your solution to this, which is going to be 5/3, how do you know it works? Well, you plug 5/3 in for x and you verify that it's true. Okay, yeah, okay. Is that clear then? Look, you're learning something new, so I shouldn't say is it clear then, because it's not going to be clear. You're going to be confused. I was yelling at the Calc 1 students earlier. I said, that's the problem. Everybody gets disheartened with this stuff, but sometimes you just got to wake up and say, damn, calculus is hard. That's exactly right. There's infinitely many solutions. You can multiply this by any number and it's going to be a solution. So that's the reason I was very careful. I put it's a solution. Not the solution, it's a solution. So the thing is, though, we don't want to guess and check. If we, guessing and checking is not efficient for anything. If there's a systematic way, we'd like to know it. And it turns out that this equation happens to be separable. And when you have a separable equation, there is a systematic way to determine a solution. So we're going to study this equation from that perspective now. So the equation that we started with, dy dx equals 10y, is an example of what we call a separable equation. And we'll see why in a second. And so these equations, or these types, or I shouldn't say these types, that's poor grammar, right? It should be this type. This type of equation can be solved in a systematic way. And the way we do it is the following. I like to call it by separating and integrating. So we'll tell you what that means in about 30 seconds, but I'll count to 20 and see if anybody wants to ask me something, tell me about their plans. If everybody's stressed out, I feel bad for you. I empathize, I sympathize, although I don't empathize because I never was a student during the Roni pandemic, so I don't know how stressful this is for you guys. Probably not as stressful for me as it is for you, but this ain't, you know, we got to make the best of it, right? Yeah. Ha! No, I told you that. You have to wait. Here's the problem. What's that? Yeah, I know. She did. Actually, it's funny you say that because I now have a reminder. Look, 6 times it's reminded me. That's that red mark says. I didn't listen. Just remember, every day I forget, I feel bad, and then you're more likely to earn an A. No. You want to learn this anyhow, right? All right. No, Becca, I did not. Not yet, at least. But I will. When would you want me to do it? I couldn't do it yesterday. I was busy. That's the problem with the Roni is like, I can't spend time here like I'd like to, right? And so it's impossible now to do the amount of work I'd like to do at home, just because like then you get guilty because your kids are like, why don't you want to do something with me? And I'm like, because I'm working. And then she'll go, you always work. And I'm like, damn. But that's the problem. So yeah, I will. I'll get to it. I promise. And by the way, I should mention it's a good time to pause. And I think a few of you have emailed me about your grades not being updated on Canvas. You gotta be louder about that so I can make sure they're updated. I know I didn't update everybody's grades. I know a few of you have yelled at me, and I gotta get on there and update. What's that? Homework grades, yeah. I try to prioritize what I think. Yeah, yes, Emily. Okay, sure. I try to prioritize, but you know, again, it's not an excuse. It's just reality. And I figure you guys got to give me the benefit of the doubt too. I know, Rebecca, I got your email and I'd literally told you last week I was going to do it that night and I had planned to and I didn't. Here's the thing. You guys have to forgive me just like I forgive you when you submit all your homework late, right? Or how I forgive you when you submit work and it's suspect and I'm like, damn, your work stinks, but I forgive you, right? It's one of those things. All right, I kid. All right, let's look at how we can do this systematically. Now, what it's going to look like we're doing is it's going to look like we're cheating, like we're just kind of making our own rules. And it just so happens that us making our own rules in this particular scenario is logically sound. And it's really what makes this work. What we're going to do is really what we learned at the end of Calc 1, integration by substitution. The change of variable that we did is really what we do here is logically sound because of that. So here's the trick. This is actually a procedure that you can master really easily and you don't even have to know what the hell you're doing. So I could teach this to like my kid. Now she doesn't know how to integrate, so she'd get stuck after that. But if she did know how to integrate, she'd be able to do this because it's mindless. Once you learn the procedure, it's not really in-depth thinking because it's sort of like a shortcut. So here's the idea. We're going to use differential notation. So you might forget what that means. So let's first separate variables. So what I'm going to do is I have dy dx, and I am going to remind myself that there's an x and a y, and I am going to take this and write it as 1 over y dy equals 10 dx. So of course you might say, well, that's how you do that. You're going to look at the left-hand side and say, that ain't a fraction, O'Grady. Right? And you're right, this is not a fraction, it's notation. But if you remember from Calculus 1, we said that there's this thing called differentials that we can use. And they're like, basically we can pretend this is a fraction. And we've done this. We've done it when we did integration by substitution. I love you guys. That's exactly right. Oh, I know some of you. I love it. I'll get a damn email with 47 assignments on December 6th. And then I'll forgive you when I have to grade on that in 3 hours, right? Okay, now let's integrate. We'll write this in green. So next, integrate. So I'm going to take the integral of both sides. And so if I integrate both sides, the one on the left becomes the natural log, and the one on the right becomes 10x plus some constant. So the integral on the left is the natural log of y. The integral of 10 is 10x. And so then, of course, I have to have this arbitrary constant. A question that you guys might have is you might say, well, shouldn't there be a constant on both sides? Sure, there could be a constant on both sides. But assuming that it's different, if I put them on the same side, they become another constant. So I could write like plus c here and then plus d over here, but why don't I just note that any time I have two numbers, I can add them together. And we'll just call it c. Now remember, what are we trying to find? Well, if we go back to our original equation, we want to know what y is. What y satisfies this? So if we stick with our analogy, of undoing things, that's what you did in 7th and 8th grade. That's what you did in high school. It's what you did in algebra in college and high school. You've undone things. And so what am I doing here? How do I know what y is? Well, how do I undo what y is? Well, how do I undo what's happening to y? What is happening to y? The natural log is being applied to y. So how do I undo that? I use the inverse operation of log, which is the exponential function. So the next thing that I'll do is solve for y. So when I do that, I get y equals e raised to the 10x plus c. And this is true for any value c. And if c is 0, that's the solution we guessed. So we got the same solution two different ways. One way by guessing and checking. Another way by using some creative reasoning. Now, what this tells us is if a differential equation has a solution, it looks like it's not going to just have one, but it's going to have infinitely many. So we usually, the word we use for this is we say there's a family of solutions. It's a whole family. Yeah. Mama is C equals 0. Daddy is C equals 1. Billy C equals 2/3. Kelly is C equals -3/5. You know, pick your favorite numbers. Shobit Jr. is C equals 29, right? You know, Uncle Trump is C equals 14. I don't know. Right? Or no, he would have been 45, right? He was the 45th president. Uncle Joe Biden, he's C equals, well, he'll be 46 if things stay the way they are. Any questions about this? So why are these called separable equations? They're called separable equations because you can actually separate variables. You're not always going to be able to do this.
I would be right even if I did like, I just kept the integral in sign without doing 1 y dy, right?
Yeah.
Become y equals to 5y squared.
Wait, say that again?
If I put those integrate and signs, right? In the first equation,
Yeah.
dy over dx equals to 10y. So that would be y equals to 5y squared, right?
But you can't do that. Notice the only way I can integrate both sides is once I have it like this. Okay, so that's a good point. You can't, it makes no sense to take the integral of both sides here because you don't have the differentials. Do you understand what I'm saying? It doesn't make sense to integrate this because what are you integrating it with respect to? Notice once I write it like this, now I can integrate with respect to a specific variable. Do you understand that? Yeah. And really, like I said, it's more aesthetically that it works. The actual deep reasoning why it works is you're using a change of variable on this. And you can read about it in the book if you want, but I don't know that that's worth our class time to do it. One of the reasons we teach differential equations in calculus is because some of you will see them and have to know how to solve them in other courses. If you want to understand why the solution exists and the actual mathematic theory behind it, then you take more math classes, right? That's sort of the idea. By the way, take it with me in the spring. It'll be so much fun. Differential equations, sign up. Actually, the less of you sign up, the less grading I have to do. So maybe don't sign up. What's that again?
I already did mine, so.
Did you?
Yeah.
Well, you need to take it. Yeah, I never understood why people, like, I took every class I could just because it was paid for anyhow, right? Some of you don't want to take anything unless it's on your little thing, but it's not like you're not paying for it anyhow. It's already paid in your tuition. When I was in grad school, I would take everything. Of course, I wasn't paying for it, but I love to learn. That's how I roll. All right, so a couple things we should say. So let's give some definitions. So we call y equals e to the 10x plus c the general solution of the differential equation. So for each real number C, we get a particular solution. And by the way, the way we've written it is not the sort of the convention. It's convention to write instead of writing e to the 10x plus c, we can write this in a much cleaner way. So it's convention to rewrite e to the 10x plus c as e to the 10x plus c, and then use your properties of exponents. And then just give, so the property of exponents that you learned many, many moons ago says you can break it like this, and then just call e to the c another number. Because look, e is a number, c is a number. If I take a number and raise it to another number, I get a new number. So let's just call it a. This is sort of the convention that we choose. So thus, y equals ae to the 10x is the general solution.
Wouldn't that make a difference?
Say that again?
When you go to the previous like that, wouldn't that a make a difference since it's a number? So 10 multiplied by a will be.
Yeah, it's just to be another number. That's right. Yeah, that's correct. So you could check it yourself. Plug this in for any a. Take the derivative of this. You get 10a e to the 10x. So it works. It always works. So one of the things that happens with differential equations is let's assume we're modeling something, some physical phenomenon. Let's use the bacteria in a petri dish. And so it's often common that the differential equations, we use different letters. We might, instead of using x for our independent variable, we might use t for time. And because of that, let's imagine we're doing experiments and we might have an initial value of something at a given time. The number of bacteria in a petri dish at time 0, right? The temperature of an object at time 0. The amount of money in my fund on the first day of the year. So we often have a differential. What do you mean does a substitute as c? No, I mean, they're just, A can be any number, Emily. It could be any number at all. C can be any number at all. What we're saying is e to the power c's got to be a number. Let's just call it a. We could call it anything. You want to call it cat? You want to call it dog? You want to call it can? You want to call it key? I don't know what you want to call it, but most textbooks and people will just call it a. Well, I didn't place it somewhere else. Here's the reasoning. This, again, I'm rewriting this. The exponent has a sum in it, and one of the exponent rules says that I can write the exponent that is a sum as the product of exponents. This is an elementary exponent property. You saw it in algebra class years ago. You would probably write it differently, but all I'm using is like 2. I'm using like 2 to the 5 plus 6 is the same as 2 to the 5th times 2 to the 6th. That's what I'm using. So that's the property that I'm taking advantage of here. You don't have to do that, but most books and most things you're going to encounter in the study of differential equations are going to write it like this, not like this. I mean, this is just aesthetically more clean than this, that's all. All right, so oftentimes differential equations have what we call an initial condition. So, for example, we may want the solution of our original equation, dy dx equals 10y, that satisfies y of 0 equals, say, 6. So you know, maybe I'm studying a population of fish, and I say, all right, I start with 6 fish. How many fish am I going to have in 3 days, in 30 days, in 5 years type thing? So if we look at our solution, we'd like to know what value of A gives us the solution that goes through the point 0, 6. So let me go to Desmos and elaborate on this a little more. So let's look at our solution. Our solution was y equals ae to the 10x. Now, of course, if I'm going to just let a range between values, so if I do that, if I let a be different values, I get different curves. These are all different solutions. I want to know the value that goes through the point 0, 6. That's what I want to know. So if I come up here and I'd like to know which one is going to get me through at 6. And so there's a systematic way of figuring this out. So to do this, we set x equal to 0 in our solution. So on one side, we have y equals 0, and on the other side, we have ae to the 10 times 0. Now, if you look at this, what is y of 0? Well, y of 0, we know that we want it to be equal to 6. And over here, we get a times 1. So for this to be true, this forces a equal to 6. So what we would say is we would do the following. We would say the particular solution passing through 0, 6 is y equals 6e to the 10x. So one of the things that we're often studying in applications of calculus, whether it's chemistry, physics, engineering, economics, finance, whatever it is, we typically have a differential equation paired with an initial condition. And there's a name for that. It's called an initial value problem. So a differential equation paired with an initial condition is called an initial value problem. And we typically use the acronym IVP. So let's do an example of that. Show you what we mean. So here we go. And please stop me if you have a question or a comment. So we're going to solve the initial value problem. They often are written with a bracket. We might have dy dx equals, let's say, 6y squared x. And then the initial condition is when you plug in 1, it should spit out 1/25. Okay, so we're going to do the same thing we did in the previous example. First, we'll solve to get the general solution, and then we'll get the particular solution. So the first thing we'll do is get the general solution. Then the particular one. So we begin by separating. So when I separate my equation, I get 1 over y squared dy is 6x dx. Okay, so once you separate, next you can integrate. So when I integrate the left-hand side, it has to be equal to the integral on the right-hand side. And on the left-hand side, you integrate to -1 over y. The right-hand side integrates to 3x squared plus c. So what we found is we found what y is going to be. We didn't solve for y yet. We have one more algebraic step, but all intents and purposes, we're done. We just have to rewrite it. So this is how y and x are related. So this is exciting. So let's solve for y. How do you solve for y? Well, this is, for many of us, this is algebra nightmare. You just multiply both sides by y and divide both sides by 3x squared plus c. So some of you might have called this cross multiplying, but you need to think about the actual algebraic reasons it's true. So we solve for y to obtain y of x. What does it equal? Well, it's going to be -1 over 3x squared plus c. So this is the general solution. If you were to differentiate that function and plug it into the original equation, you would see it's a solution. Okay, so to get the particular solution, we need to use our initial condition. So we set x equal to, what was it, 1? Yeah, x equal to 1 and y of 1 equal to 1/25. So you're left with 1 over 25 on the left-hand side has to be equal to -1 over 3 plus c. And that implies that c has to be -28. So you could solve it the old-fashioned way, or you can just look at this thing and say, what do you need the denominator to be? You need it to be 25. So how do you get that? If you set c to -28, it's a true. So I'm actually solving this for c by just recognizing the solution is somewhat obvious. And so the particular solution to the initial value problem is y of x equals -1 over 3x squared minus 28. Isn't this fun? So much fun, I didn't know what to do with myself. So look, let's remind ourselves of what we need to remind ourselves of. This is not easy stuff. But solving separable equations is much more systematic and procedural than some of the stuff we've been doing. If you understand separate and integrate, well, as long as you can integrate, you can solve these. It's not the same as when we were doing these power series and we were doing these series tests where you have to really think about what you're doing. Here, you're just doing a procedure. So in many ways, this is mundane. It's not very thought-provoking. And frankly, software can solve these for us anyhow. What's interesting, though, in the real world is most differential equations we encounter can't be solved. We say these are analytic solutions because we're doing the calculus by hand. But oftentimes what happens, I've concocted these examples so that you can actually integrate both sides. What if you weren't sure how to integrate it? Well, then you can't do it. Or maybe you can't integrate one or both of these. And so in the real world, we have other methods as well. But of course, if we can get precise, exact answers, then we want them. And it turns out that many important differential equations happen to be separable. For example, many equations that are used to study spread of disease, Roni and stuff like that, are separable equations. So before we leave, I just want to point that out. And by the way, well, I shouldn't say by the way, let me just do it. So if you go to infectious disease modeling, for example, you have all this stuff you can read about. And some of the most basic models of differential equations that are used to study disease spread are separable equations. One of the more famous differential equations is what's called the logistic equation. And it too is a basic differential equation for understanding how populations grow or decay. And this differential equation turns out to be separable. So it's in many ways, it's a simplified model of what happens if you have a population and you want to ask, how does the population evolve over time? Any comments or questions? So I only point that out, not that we're going to be studying infectious diseases. I'm only pointing this out because of the fact is, separable equations are a very important class of differential equations. And they're important for a few reasons. One, lots of real world models are separable. And also we can solve them by hand. And so you're going to, maybe not in this class necessarily, but in certain classes, you'll find that you can't solve differential equations by hand. So then you have to come up with more sophisticated approximation methods. And those are fun too, and they're fine. Did you guys do like electricity in physics yet? Like Ohm's law and all that? That's a differential equation. Oh yeah, absolutely. Yeah.
So we never thought of this in Calc here.
Are there differential equations in Calc 3? No.
So why did it show that it's a prerequisite of Calc?
Because in differential equations, well, there's certain things in Calc 3 that are useful to know when you take differential equations. They're not necessary, but they're useful. And by the way, these are what we call ordinary differential equations. They're the most basic type. The many that show up in things like engineering and things like physics, where we're talking about fluids and gases. These are much more complicated equations. Okay, does anybody have a question or a comment about this? So look, if you take a differential equations class, we go way more in depth of separable equations. But what you need to know from today is that there's a thing called a differential equation. One type is one that you can actually separate the variables. You can't always do that. Not every differential equation can be separated. So you need to understand that. And we'll talk about another class that is not separable that we can actually analyze. And we'll do that next class. So some key ideas that you should think about moving forward. Good news. Separable, let's spell, equations are, relatively speaking, not easy in the sense that they're like adding 4 and 5, but relatively speaking are easy to solve and analyze. Bad news. Most differential equations aren't separable. So, for example, hit my computer. We can't separate X and Y here. So what if I had something like dy dx plus the second derivative equals, say, cosine of 5x. You can't get all the x's on one side and all the y's on the other. Now you might say, well, that's a little different beast, O'Grady, because there's a second derivative involved. And that's true, but I can give you one with the first derivative that's also not separable. So let's just give you another example. What if I just had dy dx plus xy equals, say, 3x squared? So you can't get the x's and y's separated there. So we have to come up with another strategy. I mean, you could try. You look like you're thinking you can.
No, so the way I thought of, right? I thought that X and Y were
They are multiplied, yeah.
So I didn't figure that plus. So I just took them down and I'm like 3x squared over yx.
Yeah.
And I found out that it's 3 over y. And I was like, it's possible. Then I realized it's a plus. So it goes to the minus.
That's right. So you're correct. This plus term sort of really throws a wrench into everything.
If the plus was not separable.
Well, if there was no plus here, you could definitely separate. Yeah, if this were a product. So yeah, we'll talk about this stuff going forward. Yeah.
What if the one you got on top, right, of the cos 5x, you just remove the first part and it becomes the second derivative equals to cos 5x.
Well, if you got rid of this, right? But you can't just get rid of it.
No, is it separable? Like if you,
Oh, if it was the second derivative,
yeah.
second derivative is tricky. You got to be careful. And I don't want to get into that, but if you got rid of this or this, would it be separable? Well, if you ignored this piece, if you deleted this piece, then it's separable, right? Because you can get the x's on one side and the y's on the other. But really, it's not even necessary to do that because you can just integrate if this were gone. Second order equations are a little trickier. Second order means that there's a second derivative involved. We're not going to talk about them in this class. They're a whole new beast. We spend time on them in the actual course. All right. If you guys don't have any questions, I will talk to you Thursday, if not sooner. All right, everybody. Thank you very much and take care. Be safe. Let's end this party.